Hello. Okay, here's a question on the flywheel. So this flywheel's got a mass of 90 kilograms. So it's like this. So it's a bit like that. Hang on, no. Flywheel is 90 kilograms, so the mass is 90 kilograms. Diameter, so diameter is 0.2 of a meter. It's going from 12 up to 27. So it starts off at 12 RPM and goes up to 27 RPM in 40 seconds. So the load on the bearing, so we'll have a bearing in there. Say there's the bearing in there supporting it on a shaft. And is 5 newtons on there. That's the force to overcome the bearings. And the friction is 0.03. Okay, so we've got to work out A, B, and C. We'll do A first. The overall applied torque needed to accelerate the flywheel. So we need to apply a torque. So we've got to apply a torque. That's how we get this flywheel to move. There's two forms for torque: force times radius, or we can use torque is inertia times by angular acceleration, because this thing is being accelerated. So we need to find the overall torque. Move this down a bit. So the overall torque that we need to apply. First of all, we've got to think about the total torque. So we're going to have this TT is total torque. Okay, and we've seen before that the total torque is going to be TI plus TF. TI is torque to overcome inertia, and TF is the torque to overcome the force. So we'll do TI to overcome inertia first, because we can do that, because it's going to be this. I times that. And then the torque to overcome friction, we're going to be using coefficient of friction, the force on the bearings times by the radius. Okay? R just means radius of the flywheel. So we'll do, what should we do first? We'll do torque to overcome inertia first, sorry. Torque to overcome inertia. So we're going to do in TI, torque to overcome inertia is inertia times by angular acceleration. Now, it's a flywheel, so we can do inertia. Inertia of a flywheel is a half times the mass of the flywheel times by the radius squared of the flywheel. Let's get a different color pen. So it's quite easy because we know that half is a half. The mass of the flywheel is 90 kilograms. So I'll do times 90 kilograms, and the radius is half the diameter, which is diameter is 0.2, so radius is 0.1, so it's 0.1 squared. Whack that in your calculator and you'll get something like 0.45. 0.45 kilograms per meter squared. Okay. So that's the inertia which we can put in there. Okay, put that in there. Inertia. Now we need to find the angular acceleration. We need to find the angular acceleration, which we can do because we know that this flywheel starts off at 12 RPM up to 27 RPM in 40 seconds. So we know the speeds or the velocities and we know the time. So we can find the angle of acceleration. Okay, so it starts off, omega 0 starts off, initial is 12 RPM. And the final angle of velocity, so I put 0 and a 1, look, that's starting, that's final. It's been revved up to 27 RPM. Starting and finishing. We can't use RPMs, we've got to be in radians per second, so we need to multiply this number by 2 pi over 60. Okay, so we've got to multiply 12 by 2 pi over 60. That will get it into radians per second. And we'll multiply this one, 27 times 2 pi over 60. Because we can't be in RPM, we've got to be in radians per second, and this 2 pi over 60 does that for us. So 12 times 2 pi over 60 will give me 1.26 radians, rads, look, per second. And then 27 times 2 pi over 60 will give me something like 2.827 radians per second. So now we know it starts off at that and it ends up at that. We've got to find the angle of acceleration. So it's the change in that speed over 40 seconds. So we remember this equation. Okay, different color pen. So if you remember this equation, anybody know the equation? Anybody know it? So omega 1 equals that plus that. That's angular motion. Remember, we've done it before where we've done linear motion, and we're going to get this. So if you like this better, use this one. V equals U plus AT. Same thing. V is final, U is starting, A is acceleration, and T is time. This is just the angular version of it. So we can rearrange this. We can rearrange this formula to now find our angular acceleration. So it's going to be this. Omega 1, which we know, take away omega 0, which we know, divided by the time, which we know. So omega 1 is going to be, where are we? 2.827. 2.827. Take away omega 0 starting is 1.26. Take away 1.26. We divide that by the time, which we know is 40 seconds. This will give us the angular acceleration of this flywheel in radians per second per second. If you put that on your calculator, you'll get a number that looks a bit like this. 0.04 radians per second per second. So now we know angular acceleration, which means now we can find the torque to overcome inertia, which is I times by angular acceleration. So the inertia from before was 0.45 up there. So we'll do this. 0.45 times by the angular acceleration, which is 0.04. So that gives me in a calculator something like 0.018 Newton meters. That's to overcome inertia, the torque to overcome inertia. We also got to now find the torque to overcome the force on the bearings, which is going to be coefficient of friction, load on the bearings, and radius. And then we can add that to it then, because we're using this formula up here. Look now, where are we? Here, look, here. Okay, so This here is coefficient of friction, which we know is 0.03. That F there is the force on the bearing, which is 5, and R is the radius, which is 0.1. So we'll work that out and then add it to what we've just done, and that will give us the total torque. That will be part A done. So this is going to be, now we've got 0.03 times by the force on the bearings, the load on the bearings, which is 5, and the flywheel radius was 0.1. This is the torque to overcome friction. Put that in your calculator and you get something like 0.015 Newton meters. That is the torque to overcome force. So the total torque is just them two added together. So the total torque is that one, which we know because it's there, plus this one, which we know because it's there, 0.015. So we'll add them together, and this will be the total torque to get this flywheel to move. So it's going to be 0.018 plus 0.015. 0.015. Dun, 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 dun. The total torque is going to be 0.033 Newton meters. That's the answer for part A. That's the total torque. There, look. The total torque to accelerate the flywheel, to overcome friction and everything else. The answer is 0.033. That's part A. Part B is next. So we've got now part A done. So now we need to do part B. Hang on. Let's get rid of that. Let's go up. Part B is, so we've done the overall applied torque. We've now got to do the work. So part B, work done accelerating the flywheel to 27 RPM. So that means how much energy do we need to put in? How much energy is that torque providing to accelerate that flywheel, which is a bit of metal shaped as a wheel, up to 27 RPM? Okay. So part B. Part B. So work done. Work done. Okay. So we know from previously that work done in angular motion is total torque, which we've just worked out, look, times by angular displacement. So total torque, total torque multiplied by angular displacement, That's going to be in radians. So how many radians has this flywheel gone through in accelerating up to 27 RPM? Right, well, there's a formula for that because there's always a formula. So angular displacement is going to be this. We've seen this before. Angular displacement, starting angular velocity times by time, plus a half angular displacement times by t squared. Okay. In linear velocity terms, when we did that, that's the same as this. S equals ut plus a half a t squared, where s is our distance, so angular displacement. Omega naught is our starting velocity. T is time. Half is just half. Angular displacement, t squared. So we'll just put them numbers in. So we know that the starting angular velocity is, it's up here somewhere, omega 0 is 12 RPM, 1.26. So we'll be using 1.26 radians, rads per second. We know the time is about 40 seconds time. So put 40 in there, 40 seconds. And then we need to know the angular acceleration, which we worked out up here somewhere, which was here, like angular acceleration 0.04. So nothing of a surprise here. I'll put them numbers in, and that will give us how many radians this thing's gone through. Is that better? I don't know. Is that better like that? So here's the formula. So angular displacement is omega naught, which is going to be 1.26. Don't do it in RPM, do it in radians per second, times by the time, which is 40 seconds. So it's all of that plus 1/2 times by angular acceleration, which is 0.04, times by 40 squared. Whack that in your calculator, and this will tell you how many radians it's gone through in that time. Well, you should get something like 82.4 radians. That's our angular displacement. Okay, it's not linear motion. Linear motion would be 82.4 meters. Angular is radian, so it's gone round 82.4 radians. Now, we can simply do this now. So work done is total torque, which we know, times by angular distance, which we know. So total torque is 0.033. 1 before 0.033 times by angular displacement, which is 82.4. This will tell us how much energy we need to put in joules to do that. This is part B now, don't forget, part B. Put that in your calculator and you get something like this, 2.72 perhaps. 2.72 joules. That's how much energy we need to put in. Okay, that's how much energy we need to put in. So that is part B. Here's part B. And then part C is coming next. So part C now is the final lap. So we've done all the hard work really. So part C is, where is it? The power dissipated in accelerating the flywheel. So how much power do we need to accelerate that flywheel? Okay. So power, we all know what power is. So power, he's moving to me. So power is work done divided by time. Power is how fast you do work. How fast you do work. So it's work done divided by time. My favorite joke is, what is the unit of power? And you should say watts, because watts is the unit of power, or joules per second, but it's not a good joke, so you've got to say watts. So power is work done divided by time. We know the work done. It's up here, look, 2.72. It's going to be 2.72, something like that. Divided by the time, which is up here, so we're 40 seconds. So that's it, 40 seconds. Divide that by 40, gives you something like 0.07. 007 of power. Part C. Part C done. Happy days. So that's it. So we've gone through now A, B, and C. There we are. So that is how much torque we need. That's how much work done we need. That's how much power. So if we've got a flywheel, we know how much torque we need to apply to accelerate it up to 12, up to 27. We know how much work done, how much energy we need to put in, and we now know how much power. That's it. That's all we got to do. So for this question, it's over and out.